This video is designed for teachers participating in our quantum professional development for physics and chemistry high school teachers in Duval County Public Schools. I'm also going to make this video and the notebook available for any viewers of my channel who would like to learn a little bit about how to integrate quantum mechanics into a high school context using computation. So in order to do that, we first have to learn how to do computation at all. So the modules for this professional development are written in what's called Jupyter Notebook. Jupyter Notebook is this wonderful environment where you get to blend the code that you're working with a report-like documentation. So imagine you have a lab report that has code embedded in it that you can run. So you can have a discussion, you can have code embedded, it produces some results, you can then write a section of the report that discusses those results, et cetera, et cetera. You can go back and forth between the report format and the coding format seamlessly. So we love using Jupyter Notebook at the university level, and they've had a lot of success with using these in the high school level as well. So we start off this first module answering the question, why computation? Why bother incorporating this third branch of physics in addition to problem solving and labs? Why add this third branch to your course? Well, to put it simply, because your students are going to be doing it at some point. This is data from the American Institute of Physics, where they asked recent physics bachelor graduates employed in the private sector, what do you do on a regular basis in your job, either daily, weekly, or monthly? And if you look over here in this second block, programming for folks employed in engineering is right around 75% use programming at least monthly. And then in the computer science field, it's nearly 100% that they engage in some sort of programming at least monthly. And so to the degree that we don't include computation in our courses, we're actually doing our graduates a disservice when they get to the job market. And so any exposure we can give them to programming, even just communicating to them that computation is a thing in STEM fields, is really worthwhile, spending any amount of time we can on. So in order to help you get accustomed to this, we have this Jupyter Notebook, Module 1, Intro to Jupyter. No quantum in this one, literally just how do I use this Jupyter Notebook? How do I do some basic operations in Python? Because there's actually a lot that you can do in a high school context just with a few simple operations in a Jupyter Notebook. So the first thing we want you to learn and that we want you to pass on to your students is that Python can calculate for you. We really want to help spread this vision that programming is really an extension of a graphing calculator, right? So students start with a 4-function calculator, they graduate to scientific calculator, then they get a graphing calculator. This is really the next step in that development. And really in my classes, I encourage my students to use Python or to use a Jupyter Notebook instead of a calculator, because it's so much easier to go back and review what they've done. So what you'll see here is a text cell that just goes over what we're doing in this section. I'll let you read it as you work through the module. But then we come to our first code cell. A code cell, you can see it's grayed out here, is something you can run by pressing the play button here. It will take it a second the first time to connect to Google's Jupyter server. And what you've got here is the output of this code cell. So every time there is a print command, we have output printed to the screen. So for example, this first one tells me print 3 plus 2. Lo and behold, I get 5. Next one, print 3 minus 2. Lo and behold, I get 1, et cetera, right? So I can use any of these operations that I want. And what you'll notice is that Jupyter Notebook will follow the order of operations. So like when I have 3 times 2 plus 2, order of operations tells me that I need to do 3 times 2 first. So I'll have 6 plus 2 gives me 8 there. Lo and behold, I get 8. Similarly, when I'm doing division, I'll have 3 divided by 2 plus 2. It even converts it to a decimal for me, just like a graphing calculator would. What I want you to notice about this first and foremost is that Python's going to execute each of these lines in order. It starts in line 1, 2, 3, 4, 5, etc. So that's why you notice that they come out in the same order that we type them in here. I've even got a demonstration of that here. We just do print 1, 2, 3, 4, 5, and we get 1, 2, 3, 4, 5. Now you might notice that these lines that begin with a hash mark are colored green. These are what we call comments. The Python is going to ignore anything that starts with a hash mark. That's just where you can leave a note for yourself. It's not going to be interpreted as code. It's just going to be passed over by the Python implementation. So then we have a checkpoint here where I ask you to just edit the code, right? We never want you to have to write code from scratch. We're always going to give you a code to start with so that you don't have to stare at a blank screen for several hours. And we just ask you to change some of the computations. You can carry out any combination of addition, subtraction, multiplication, division. If you really want to get fancy, you can even do an exponential or a power by doing a double asterisk. So if you want to do 3 squared, you type in 3 asterisk asterisk 2, and that'll do a power for you. And we just want you to convince yourselves whether Python obeys order of operations. And then we want you to think about how is this similar to using graphing calculator and what advantages do you see of using this editable format over a graphing calculator. So the next thing we're going to learn how to do is store those numerical values in variables. So just like what you have in your math class, you can say x equals 3. You can do the same thing in Python. You get to pick the variable name and you get to tell Python what it's equal to. So for example, in this code cell, I'm taking the value of 2 and I'm storing it in the name A. Think of this like saving a file under a certain name. Anytime you open the file, it's going to open that information based on the name that you clicked on. So for example, here when I say print A, it's going to show me 2, right? And then I have A times A is going to give me 4, A times A times A is going to give me 8, then 16 for A times A times A times A. And the beautiful thing about this is I can just make one change to this. So I can make a change for this to 3, and now I'm getting powers of 3 instead of powers of 2. And literally I can make this anything I want. I can make it a half. Now I'm getting the powers of 1/2 there, which is pretty awesome stuff that I can run the same calculation using a different numerical value. And so that's what we ask you to do here in this checkpoint is just change that one value of A, and all you do is change line 3. Oh, I should mention, I make reference to line numbers here. If you're not seeing line numbers over here, you can access that in Tools, Settings. And then under Editor, you can tell Google Colab to show line numbers. I forgot to mention that in the write-up, so I'm adding it here in the video. What's really neat about this process is that I can change a variable's value. I'm allowed to reassign a value to the same name. Again, going back to the comparison of file names, this is like when you save a new version of a file. Right? You hit save, you're writing over the earlier version of that file. So like, for example, in this example, we've got A equals 7, and then we say A equals 2 times A. Now, this would get you in a lot of trouble in a math class, right? Unless A is equal to 0, that's an illegal thing to write in your math class, right? But really what it's doing is it's saying, I want you to calculate 2 times A. So calculate 14, take that 14 and now store it under the name A. And it really doesn't matter that it's using A here and A here because it's going to do the right side first. It's going to do the computation first and then save that under the name A. So it's just saving over the previous version of A here. And so this next code cell walks you through an example of that. This is how you might, for example, calculate 4 factorial. Is I could just store 4 under the name A, and then I want to calculate my factorial. So I'm going to multiply it by A minus 1, then A minus 2, then A minus 3 until I get down to a value of 1 that I'm multiplying by there, which is pretty cool. Then next there's a checkpoint where we ask you to use this type of variable reassignment, calculate the factorial of 6. So what would you need to do in order to modify this to get 6 factorial instead of 4 factorial? Now, what will inevitably happen when you are working with a code is that there's going to be a mistake. It happens. In fact, making mistakes is the best way to learn how a code works, is to see how it's not working. Whenever you have an error, Python's going to give you an error message. So like, for example, I was typing up this while working on a tutorial, and I had forgotten to include a parentheses on here, right? I closed my parentheses here. I never closed the original print parentheses. And it gives me an error message that says unexpected end of file while parsing, meaning you left something off, Brian. And so I went back up and I just looked for what I might have left off, and I see I left off a parentheses. I go back and add it. I rerun the code. and I don't get the error message anymore. We've got some general advice here. Unfortunately, reading error messages is not really something I can explicitly teach you how to do. It really just comes with practice, and that's okay. That's how we all learn it. But I do have some general guidelines here, and then I have a checkpoint here for you to try out reading and interpreting an error message, and then finding where the error is and how you can fix it. Now, since we're headed toward working with quantum mechanics, we need to review how Python handles complex numbers. Complex numbers are essential in quantum mechanics. They're responsible for a lot of the weird stuff that ends up happening in quantum. So just as a refresher, complex numbers, your students might see this in an Algebra 2 pre-calculus class. It really depends on the teacher and the curriculum and how that year is going. But complex numbers are something that high school students can understand, and that they actually can find pretty intriguing if you can show them what they're useful for, which we're going to do with quantum mechanics. So as a reminder, complex numbers involve the square root of -1, which when you're first learning square roots, your teacher tells you is not allowed, but then eventually you learn, yes, it is allowed. We just have to treat them differently. We're going to be using the symbol J for complex numbers instead of the usual I that you might have seen in a math class. The only reason for that is that Python adopts a convention of using J instead of I. It means the same thing. I'm just going to use J in the notation here just to keep it consistent. So anyway, J equals -1 is the imaginary unit. It's the thing that makes a number imaginary or complex. So any complex number Z can be written in terms of two real numbers, a real part X and an imaginary part Y. Two complex numbers are equal if and only if their real parts and their imaginary parts are equal. So if you have Z1 equals Z2, then X1 equals X2 and Y1 equals Y2. That's the only way those can be equal. We say that the complex number Z has 2 degrees of freedom, meaning it has 2 different values that you can specify in order to get a unique Z. One thing we'll be doing a lot with complex numbers in quantum mechanics is taking a complex conjugate. So you call a complex conjugate with a star, so it's Z star. All you do is take all of the J's and flip them into negative J. So wherever you have a positive J, you make it a negative J. Wherever you have a negative J, you make it a positive J. So complex conjugate always takes you back around to the previous one. And then another thing we'll be doing frequently is calculating a modulus. This is where you take Z star times Z. So take the number, multiply by its complex conjugate, and take the square root. If you work that out, you've got X plus JY times X minus JY, which when you simplify it just comes out to square root X squared plus Y squared. Now, if you look, that's the Pythagorean theorem. This is why I know your students can do this, because the hardest thing in complex numbers is the Pythagorean theorem, and you're already teaching that. And there's a reason for that. Complex numbers map perfectly onto two-dimensional vectors. So if your students can do two-dimensional vectors with an X component and a Y component and a magnitude, they can do complex numbers. It's just different notation to get at the same thing. I've got a link to a tutorial here just to review how these things work in the complex plane, but then we'll get on to how Python handles complex numbers. All you do is put in a J next to the number. You notice there's no multiplication asterisk there. If you put an asterisk there, it's going to ask you what J is equal to. But as long as you just put number and J right next to each other, it's going to interpret that as a complex number. So like if I go to print a complex number, it's just going to look exactly like that. It's going to look like 3 minus 2J. If you end up with a decimal on there, just have the decimal and then J. And then here we go through a lot of the operations that Python can do with complex numbers. It can add them just fine. It can subtract them. It can multiply them. You can access the real part if you use the NumPy library. We just import that family of functions up here. That's just an external library of functions that we can import. You use np.real to get the real part, np.imag to get the imaginary part, np.conj to get the complex conjugate, and np.abs to get the modulus. So we go over, I want to point this out, we go over the math up here of how to do this, but our goal is really to get students to thinking in terms of how can I get the Python to do this for me so that they're not being bogged down with remembering all of the math, right? They're going to be calling functions much more than they're going to be working it out by hand. Another important thing we'll be using throughout these modules is arrays. An array is a list of items. So remember we were storing A equals 2 earlier. Well, what if I want to store multiple values under the name A because those values all go together? So we give you an example of this here. You can create an array, just straight up list some numbers. So all of these numbers get stored under the name student heights. And when you want to access that information, like I can print the entire array, it will give me the entire list, or I can just access a single value and it will give me that one value. Now you might notice that, let's run this one here. You might notice that I'm asking for student heights of 1 and it's giving me 45, which is actually the second element. That's because Python starts counting arrays at 0. So this is actually element 0, element 1, element 2, element 3, etc. It takes a little while to get used to, but you eventually get used to it. You start counting at 0 instead of start counting at 1. And then this is a checkpoint here for you to work through some of that and discover that Python starts counting at 0. Again, we give you an example of some errors to watch for. The most important thing to watch for when you're working with an array is trying to access elements that aren't there. So for example, here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I have 14 elements. If I were to try to access element 17, I'm not going to get it. Right? It doesn't exist, right? Because I haven't given a 17th element. That's the main error to watch for there, is trying to access an element that doesn't exist. Now, of course, it's wonderful to have Python do all this computing for us and spit out a bunch of numbers, but it is so much easier to look at results graphically than numerically. So this next code cell just walked you through how to create a simple line plot, like you probably already have students doing on a graphing calculator or an Excel or your favorite, plotting package. This is how you do this in Python. First, you create arrays. This is why we need the arrays, is so that we can plot the information. You just create an array of x values, then you create an array of y values. We're just going to make a graph of an exponential, a Gaussian function here. And then you set up the plotting function, and you just tell it to plot the data that you have here. So when I run this, I'm going to end up with a graph here. I can add more data if I want to. If I wanted to create a z set of data, I can then add my plot.plot x comma z, which is exactly what we're going to have you do down here at the checkpoint. So you should be able to get two plots laying one atop the other there. And then there's all sorts of graphing commands that you can use. The two most important are going to be set and legend. We're going to ask you to Google search for these. So like, for example, if I go to matplotlib, plt.set, pyplot.set. There we go. That's what I want. Then I can look in here, set and get properties. And here I've got information on how that set function works. Same thing with legend. I can look up how to create a legend there. Again, you can end up with some errors on the graphing. Usually, again, if the arrays don't match in size, that's just something to look out for there. And then we conclude with a section on bar plots. This is going to be used when we start talking about probabilities and histograms, all that wonderful stuff in quantum mechanics. So that's an introduction to Python in Jupyter Notebook. This is the essentials of like everything you need to be able to do with this. If you take it one piece at a time, you will be a master at Python in no time.